Anders Sodergren, who's going to speak on Epstein's zeta function and related results in the geometry of numbers.
Thank you very much for the introduction. Thanks also to the organizers for the invitation to come to MSRI this week. It has been a true pleasure to be here. And I'll talk to you about the Epstein zeta function and some problems that I like to think about. The plan is roughly like this. I'll introduce some notation and try to motivate some of the problems I'll talk about via discussion of minima of this zeta function. Then I'll talk about some value distribution results that belong to this discussion and look at some key aspects of the proofs here in order to view forward and see what the next steps should be, and that's where the talk should end. So we're somewhere close to the work in progress at the bottom here. Okay, so I'll use the notation xn to denote the space of n-dimensional lattices. And for this talk, it's not very important, but I'll use that you can identify this space with the homogeneous space, SLN-R mod SLN-C, in a way pointed out here on this slide, how you do this identification. And the upshot of this is that you can use the structure that's present on the homogeneous space, and for this talk, it will be important that you have a natural measure on this homogeneous space coming from Haar measure on SLN-R, so that we have in some sense, a canonical probability measure that I denote mu n, and that will be used a lot in this talk. So xn equipped with mu n is a probability space, and if I say something like a random lattice, I mean that I pick a lattice in xn at random with respect to this measure mu n. Okay, and then it's this zeta function. How do I define it? So for a lattice in this space xn and a complex number s of real part greater than n halves, it's defined as a sum over non-zero lattice vectors. And what I sum the length of the vector to the power minus 2s. So I hope that it's quite clear that this is some sort of higher dimensional analog of the Riemann zeta function. And it was actually introduced as such by Paul Epstein. He thought that this might be the most general way to write a zeta function. As a generalization of the Riemann zeta function, it has many of the properties of the Riemann zeta function. It has an analytic continuation to the complex plane punctured at the point n halves, where there's a simple pole. And it has a functional equation of a form that is sort of similar to what you might be familiar with from other cases. It relates s to n halves minus s in this normalization, and also the lattice L to its dual that I denote by L star. So there are some clear similarities with standard cases. However, one should note that this function is, of course, of interest because its relation with classical analytic number theory, but there is typically no Euler product, and one can prove that for a generic lattice, the Riemann hypothesis does not hold. So they are truly different characters or creatures in that sense. They are not typical in some aspects. So for this talk, I will be mostly interested in the relation to the geometry of numbers, and in particular that there is a relation with the sphere packing problem. And it comes essentially from the following. So here on the blackboard, I have again written the definition of the zeta function. And if you take the variable s to be a sufficiently large real number, you see that what dominates this sum will be the shortest non-zero vector, or the shortest if there are many of the same size. So somehow, for large real s, this sum is clearly dominated by the shortest vector. And what is also important with the shortest vector is that it sort of dictates how dense you can pick your your sphere packing if you center spheres at points of your lattice. So somehow the shortest vector appears, it dominates this sum for large real S, and it's also imported in the sphere packing problem. In the sphere packing problem, you ask for the densest lattice. That means that you need a long shortest vector. And if you need a long shortest vector, then you want to sort of minimize this sum, since you are dividing by the size of M here. You want to minimize it for large real S. So that's how you sort of translate the sphere packing problem to an optimization problem for the Epstein zeta function. And that's one of the connections that I'm interested in this talk. And the Epstein zeta function appears also elsewhere, but that will be less important for this talk. For example, it's an example of an Eisenstein series, so it's of interest in respect to automorphic forms, but there are also pure mathematics interest in relation to physics and chemistry. Okay, so as I already pointed out, there is this relation between the sphere packing problem and a minima of the Epstein zeta function. And to make that even clearer, I have this theorem of Rankin, Castles, Enola, and Diamanda. So it says that if you take L2 to be the hexagonal lattice in X2, so we are in dimension 2, and L2 is, we have a picture of it here, then not only is the hexagonal lattice gives the minima for the Epstein zeta function for large S, but for all positive real S. So it's some sort of universal minima it gives a universal minima for this zeta function. And how does it relate to what I said before? This hexagonal lattice is now known to be the lattice that gives the densest packing in 2 dimensions. So it's exactly what I said before, but a little bit more, that you don't really need large real S's. You can take any positive S. And one can ask, is this sort of typical if you go to larger dimensions where less is known about the sphere packing problem? Can one still say something of this nature about the Epstein zeta function, or the relation to the Epstein zeta function? And in order to make that a little bit more precise, I give the following definition. So in fixed dimension n, I will write Ln for a lattice that gives the densest possible lattice sphere packing. So it might not be unique, and if there are multiple choices, I just pick one of them to be my Ln. And I call this Ln universal if I have the relation I had in the previous theorem, that is that the Ln gives a sort of universal minima of the Epstein zeta function, so that for all positive real S's, it minimizes the Epstein zeta function, and it minimizes as I vary over the lattice variable. That's what I mean. So the theorem on the previous slide said.
Can I just interrupt?
Yes.
You're asking this to be for all S greater than 0. So this, is it even in the region where the series does not converge?
Absolutely. So even so to the left of n halves in this normalization. Yes.
Between when S is close to 0, what sign does E and LS have?
So it's typically negative.
Okay.
Yes. And I'll come back to that. So one can now ask for n's greater than 2, is Ln universal? And it's quite easy to argue with some sort of symmetry between a lattice and its dual to see that for n equals 3, L3 is not universal. But then when it comes to n larger than 3, not much is known. But there is a theorem of Sarnak and Strömbergsson that tells you in some particular dimensions, n equal to 4, 8, and 24, at least Ln, which is D4, E8, and the Leech latches in these dimensions, has a strict local minimum at the right point. But you cannot tell that it's the global minimum as you would like to. But at least this is a sort of first step. But apart from this theorem, I don't know of any sort of results towards if there are any universal lattices other than L2 in the two-dimensional case. Anyway, Sarnak and Strömbergsson, they had this question, are there arbitrarily large n? One could maybe start with, are there other n than 2? But they ask this question, are there arbitrarily large n for which Ln is universal? And if I then already said that this theorem indicating something in dimensions 4, 8, and 24 is the only thing that is known, this is, well, an indication of that this question might be quite hard. So let's try to do something slightly weaker. So in relation to what Roger asked about, it turns out that you can, for each fixed S, average over the space of lattices and sort of find out what the average of the Epstein zeta values at this S is. And in the critical strip, the average is always 0. So the minima will be negative. And if the zeta function is defined in this way, I can have a picture that I prepared over here that if you sum positive things and you have S to be positive, a real number, then for S greater than n halves, the function will look something like this. And you have a positive residue at the simple pole at n halves, so the function will reappear down here negative. And if you have something which is always sort of giving you the minima, you will always stay negative throughout this range. But if you're positive here and negative here, you will have no zeros between 0 and infinity. So that was the sort of an observation made by Sarnak and Strömbergsson. So they sort of made a weaker form of this question and asked, okay, if you have this observation about the behavior and the relation to zeros, maybe one can ask, are there, for arbitrarily large n, lattices L for which there are no zeros on the positive real line for this Epstein zeta function? And that could be a starting point to approach the first question. And this question number 2 is something that I'll focus on in this talk as a sort of point of approach towards using, in the best possible scenario, use Epstein zeta function to say something about the sphere packing problem in large dimensions.
This question is only interested in the critical strip, right? Outside the critical strip, it's obviously positive.
It's obviously positive. So it's a question about what happens in the critical strip. And also perhaps this picture is somehow, there's a question mark here. It's really a question of what is going on in the critical strip. Yes, absolutely. Okay, so on this board here is still the question number 2 about zeros. And what Sarnak and Strömbergsson proved as a sort of first step towards answering this question was that if you studied the derivative of the Epstein zeta function at 0, so there you cannot use this form, you have to use the analytic continuation and this expression you get from that, and then you take the derivative, then it accumulates at a particular value, 1 minus gamma minus log pi. And here it's somehow of interest that this number, this 1 minus gamma minus log pi, is a negative number. That's a good observation. So adding to the picture over here, at 0, the Epstein zeta function will be negative, and for most lattices in large dimension, it sort of starts going a bit downwards. So we know something about what typically happens here. We know what happens there, but there's the big question mark. What is going on in between? And that's what this question is really about. So when I got interested in this problem, this was essentially what was known, and one could ask, okay, what does really happen in between where the question mark is in this picture? And a result of mine going back a few years gives a sort of next step in this direction. So in order to state it, I just want to tell you something about notation. I'll write Vn for the volume of the unit ball in n dimensions. And I'll let script P be a Poisson process on the positive real line with constant intensity 1/2. So this notation means that this capital N of V, it counts the number of points of this Poisson process in the interval going from 0 to V. So N of V is a counting variable. And I introduced the related variable R of V, which takes 2 times this count minus V. And this turns out to be of interest. I'll try to tell you more about it in a second. And the result is that if I'll take C1 and C2 numbers between 1/4 and 1/2, then I can, if I normalize this zeta function in the proper way by a certain power of the volume of the unit ball, then I can understand this as a random function as C varies between C1 and C2. And random in the sense that I pick the lattice at random in the space of lattices. That's where random enters the picture. And if you don't like to think about random functions, you can pick C1 equal to C2 and just get a random variable, and then the result still holds. And the result really says that I can understand this random variable, and I can even give the limit distribution as the dimension grows to infinity. And I can give it explicitly in terms of the Poisson process that I introduced at the top here. So I get the limit variable, which is a random function, and it's integrating v to the minus 2c against this measure that comes from the Poisson process. And that this limit makes sense is maybe not all that obvious, but I'll return to that in a second. But for this talk, the important thing is that as long as we stay away from sort of the midpoint of the critical strip, then I can actually give the limit distribution explicitly here. As written, I also have to stay away from the sort of sides of the critical strip, but that is not important. That can be avoided with some technicalities. One can go to 1/2, but I can at the moment not touch the midpoint 1/4. I have to stay away from there. And I phrase it like this, but I can, via the functional equation, I could also move this to something to the left of 1/4, between 0 and 1/4. That is also okay, but the midpoint 1/4 is at the moment not approachable. Okay, something about this limit. The limit variable was this integral v to the minus 2c dr of v. And to probabilist, this is sort of a well-known construction that you integrate powers towards a measure related to a Poisson process in this way. You get something called a stable distribution. And a typical instance for c equal to 5/12, if I remember correctly, gives you a graph like this of its density. So it's a little bit skewed to the left, and it decays very fast to the left, but has a heavy tail to the right. That's the typical behavior. But as you let's see approach 1/4, you get a more and more symmetric graph, and if you take a limit and normalize it correctly, you will get a normal distribution. So the normal distribution is one of the more familiar examples of stable distributions. So that should give you some sort of these limits, you can actually touch them in some sense. And as Valentin pointed out, to the right of n quarters, or in the plane of absolute convergence, this is a much easier problem. one can sort of get a similar limit result, also for c greater than 1/2 in this terminology, but it's a much easier result. And as I also pointed out, that at the moment the sort of central value is really a difficult problem that I don't know exactly what to say about. But I'll come back to that a little bit later. Yes. So returning to this question that I used as a motivation, a question of Sarnak and Strömbergsson about zeros of these zeta functions. What does this really give you in terms of this question? So the theorem that I gave on the previous slides, it tells you that if you want to ask when is the Epstein zeta function negative in the critical, for an interval in the critical strip, you can then give the limit of that probability as n tends to infinity in terms of the limit variable of the previous theorem. So when is that limit variable negative? And as this limit variable is sort of understandable and the limit distribution is rather explicit, then you can actually start to work with this limit probability and see what you get. So it's quite easy to see that the limit probability is a number between 0 and 1, strictly between 0 and 1. And if you do a little bit more work, you can actually get following theorem that if you let, in this case, C1 tend to a quarter, so you're trying to take as large a portion of the real line as possible in this corollary, then the Epstein zeta function will tend to have a 0. So it's very rare that you don't have a 0. So in the limit as n tends to infinity, typically every Epstein zeta function has a 0 on the real line. Even more can be said that typically there are a lot of zeros. So even if you would try to have the limit distribution, there would be the number of zeros of a typical Epstein zeta function would tend in distribution to infinity. So there's a lot of zeros typically. But at least this tells you something about the question, the motivating question. It tells you that if there are such lattices giving you Epstein zeta functions with no real zeros, they must be very rare. And it gives you some sort of a indication also that this slightly weaker question than question 1 is might also be quite difficult to approach. Okay, so now before I say something about the proof, I just want to return to the statement of the theorem so that we can see what really appears. So it tells you something. If you normalize the Epstein zeta function correctly, then you have a limit distribution that you can describe explicitly in terms of an integral with this measure dr of v that comes from a Poisson process. And how do these things fit together? So what I'm really want to tell you about towards the end are some approaches towards understanding what's going on at the central point. But in order to address that question, I need to tell you something about the proof. And the starting point is that if you take the completed zeta function that I denote by Fn on this slide, then you can express it in terms of incomplete gamma functions, exactly as you do for the Riemann zeta function. You express this completed zeta function as an integral of a theta function, and you divide this integral into two pieces, and they turn out to give these two brackets that are on the top of this slide. And if I introduce some notation here, so I call, say, the first bracket up here Hn, then I can write this relation sort of compactly as the completed zeta function is a sum of Hn, of two Hns evaluated at two different points at S and N halves minus s. And then I also have to remember that in the first I have L, and in the second there's the dual of L. In the region where this theorem 1 is stated, it turns out that I only need to care about one of these HNs. So it turns out that this first one will always be exponentially larger than the second in terms of n. So it's really a question about what can we say about Hn. And even that turns out to be slightly delicate, because Hn is a difference of two things. And at least the first object here is rather easy to understand. And it turns out that this second sum, if you calculate the mean value of this sum, it's exactly this expression. So the mean value of h is 0. And so the true size of the function is typically very small. It's exponentially small. So you have pieces of polynomial size, and you subtract one from the other, and the result is exponentially small. So you have to sort of be very delicate in your analysis of this Hn. So with probability 1, as the dimension grows, your function is exponentially small. And somehow you need to detect this in your analysis of this function. And I thought quite a lot about how to do this. And I wanted to essentially calculate moments, but somehow I didn't really know how to approach it. So in the end, instead of writing it as a sum, I wrote it as an integral, and that was the trick. That was enough. And I'll try to tell you something about why that is true. So Hn is this difference of a sum and another term. And what you can do is that you write the sum as a Stieltjes integral, as an integral of the incomplete gamma function against a counting function, where you count the number of non-zero lattice points in a ball of volume V. So far, it's maybe not so strange. What is a little bit the miracle in this on this slide is that if you calculate the same integral, but you change the measure from dn of v to just the dv, you get the first term here. So if you take then and create what is down here called Rn of v, which is the difference of the measure here and just regular Lebesgue measure, then you can express this entire function Hn as an integral with respect to this measure, the Rn of v. And then you have sort of transported the problem of the cancellation. Instead of having the cancellation between this sum and this first term here, now there's a question about cancellations in this measure, the Rn of v, and it turns out that I can handle the function Rn of v. So in some sense, there's nothing deep going on in this rewriting of Hn as an integral, but somehow the change of perspective is exactly what I needed in order to know what to do next. So what I can do is that I can understand the size of Rn of v. I can bound it. I can bound it well enough so that I can truncate the integral. So I only consider the integral on a finite interval. And on the finite interval, it's sort of standard expressions for the gamma function tells it that it will be some factor times v to the minus 2c. And then there's also something about this Rn of v tending to a corresponding expression in terms of the Poisson process. That one also has to work a little bit to see. But somehow that's the key in this on this slide. So I'll try to tell you more about what I think are the two main steps in order to understand this approximate equality on the last row. So the first is you need to bound the error term in the circle problem or sphere problem in high dimensions. So Rn of v tells you you count the number of points in a lattice in a ball of volume v centered at the region, and you remove the volume of the ball. So it's the error term in the circle problem. And what I can prove is that typically, or at least for almost all L, this remainder term is essentially square root of the volume. So we have some square root cancellation going on here. And in the previous talk, I thought that, if I remember correctly, it said that a true analytic number theory talk should include logs, and I think that this will be my contribution to exactly that. There will be no logs, I'm afraid. But so this is what I can prove, and this is exactly what you need in order to get the main result on the value distribution that I showed you earlier. And one can ask, okay, so how good is this bound? So for example, if you take n to be a rather large and you take some lattice that you know, say Zn, the integer lattice, the bound will be much worse than this. So for rational lattices, you cannot do as good as this. The optimal bounds are much worse. So irrationality is really important in order to get a bound of this quality. But one can also ask questions about what should be really the true size, and I'll try to return to that in a little bit when I try to mention how to extend these results to say the central point or something like that. So how do you prove this result? So the key point is a variance relation that is now on the bottom of this slide. And okay, so on the space of lattices, how do you calculate such variance? Well, so it turns out that there's a very nice formula due to Rogers it was proved in the 50s, that tells you exactly how to integrate functions of this nature, so sums over lattice points, and then the function should be of, in this case, of lattice variables, and then you integrate over your lattice. You can express such integrals in terms of integrals over Euclidean spaces. And typically, it turns out that you get an infinite linear combination of integrals of Euclidean space, but somehow it's still much better than integrating over the space of lattices. So somehow this is the key forward. And what you have to do is that you have to understand among these infinitely many integrals which contribute main terms and which are error terms, and so on. So that's how you use this formula. And I mention it because this formula of Rogers works also perfectly fine. There are versions for higher moments. They look pretty much the same, but you need much more notations. I will not show them to you right now. If you don't, we can talk about it later if you're interested. But I mention it because somehow moment calculations, like the one here, using this formula are sort of behind many of the results that I mentioned also later in the talk. So somehow this is really a key tool in working with these questions. Okay. Understanding this value distribution result, that is really what I want to focus on. There was also a question about what was the relation between lattices and the Poisson process that was in the limit variable. And the relation is the following. So if I take a lattice L, I remove 0 and look at the non-zero points, then I can order the remaining vectors by size. And I don't only take the vectors, I normalize them in the following way. So I take script Vj to be sort of the volume of a ball having the lattice vector Vj as a radius. So instead of looking at length, I rescale and look at volumes. And that's what I call script Vj. And in the same way, I order the points of a Poisson process in an increasing fashion. And then I have two sequences of numbers, and it turns out that they are related in a rather straightforward way, so that as the dimension tends to infinity, the distribution of this, the sequence of script Vj's tend to the tends to the sequence of points of the Poisson process. So typically, these sort of rescaled lengths of a random lattice, the lattice vector behaves like points of a Poisson process, and that's really the key of the results I'm talking about. And it's a direct corollary of this theorem that what was called Rn of V, the remainder term in the circle problem, tends to some related concept in terms of this Poisson process, and that should explain, if I recall you what I said about the proof of the theorem. You are interested in this function hn, you write it as an integral. The bound on the remainder term in the circle problem tells you that you can truncate and only look on a finite part. And on the finite part, you have this Rn of V, which tends to R of V in distribution. And also you know something about what happens with the incomplete gamma function, and that's essentially it. Okay, so what in this discussion does not work at the central point? So somehow the central point is the only thing that's missing from the discussion, and why is it missing? So it's really two things. So first, when I started this proof, there were not only one hn, there were two, one related to the dual lattice, and also this one that's on the screen right now. And I said that the one that is not on the screen was always exponentially smaller than the one on the screen right now. That will no longer be true if you approach the central point. So somehow there's some delicate understanding on how this hn at L relates to hn at L dual that has to be understood if you want to approach the central point. And it's also a second question is, in order to go from the first line to the second here, there was a question about sort of truncating the integral. And that truncation is much more delicate also if you only consider hn if you're on the central point. So there's at least two very important issues you need to address if you want to extend the results I've been talking about. And so the problem, if the problem is to understand the central values of these zeta functions, then, as I said, there are two, as I see it, at least two main issues. It's the truncation issue. And in terms of what I've discussed so far, that translates to something about understanding the remainder term in the circle problem. If you allow the ball you're counting your lattice points in to grow with the dimension, you need some sort of limit result for counting in larger and larger balls as the dimension grows. So that is some first issue. And then there's the second issue that you have to understand somehow the relation of this function hn at L and L dual. So there you need to understand the statistical relationship between a lattice and its dual, or at least evaluated at this function h. But something of that nature also need to be understood in order to go further. So I'll try to say something about each of these two items. So I'll start with the first one, the truncation issue. And I'll start with recalling what was needed in the previous main theorem. So there was an estimate of the error term in the Gauss circle problem, or Gauss generalized circle problem, which essentially has a square root error term in terms of the size of the main term. And one can ask, how good is this estimate? And I said something about that it's really important that you consider almost every lattice here. So you consider irrational lattices. If you have rational lattices, you get something much worse, typically. And one can ask, what is expected? And there is a conjecture. I found it in a paper of Götze, but I don't know if he was the first one. It's a rather, if you can do some probabilistic argument which is quite natural to arrive at this. So he might not be the first one. At least he's the first one that I know of that formulated this conjecture. That you should be able to do slightly better than what is the theorem on the top. So instead of square root here, you should be able to get a little bit below square root. And that should be the best possible, because Landau proved quite early on that this is he has omega results with this exponent, so you cannot do better. So if this conjecture is true, then it's optimal. Oh. Yes. Okay, and then there is this. Now I want to turn to the problem I formulated. So I said that I need to understand what's going on with this remainder term Rn as the dimension goes to infinity, but I also need the volumes to be larger and larger as the dimension tends to infinity. And what we can prove in results joined with Andreas Strombergson is that in that case, we can see a sort of central limit theorem appearing. So if you take f to be a function on the positive integers, tending to infinity, but not too fast. It must grow, but not. It must be sub-exponentially. Then we have this central limit theorem-like result, so that the error term in the circle problem at fn and the fn's grow with dimension. If you normalize them correctly by the square root here, you approach a normal distribution in the limit. So in terms of distribution here, at least this means that we can control the remainder term of the circle problem as long as the balls don't grow too fast. And when we found this result, there are sort of many questions one can be curious about related to this. And one of the things that I want to tell you about is that this result has nothing to do about counting in Euclidean balls. So you can take essentially any set that it's symmetric about the origin of the same volume as before. So if I take Sn to be a Borel set of the same volume as the balls in the first part of the theorem, and the set has to be symmetric about the origin, then the same central limit theorem result holds. So we have, here's the count of the lattice points in the set Sn. I remove the origin. I also remove the mean value, and I normalize the same way. Then I approach a normal distribution. So at least this counting result is sort of robust in that sense. It has nothing to do with Euclidean balls. And it okay. So how does this compare with the results we need for the understanding the Epstein zeta function? Well, let me first just tell you that in order to understand the Epstein zeta function, it's advantage to understand the random function you get if you consider the previous result, but you create now a random function that sends t to this random function where the t on the right-hand side sits in the argument of the remainder term of the circle problem. So you merge a lot of these error terms together, and what you get is in the limit you get one-dimensional Brownian motion. So it's a question about sort of understanding the joint distribution of the random variables that was on the previous slide. So this is what we really use when we sort of approach the problems about this Epstein zeta function. But then how good is this? Is it enough? And at the moment, it's not exactly enough. And I'm not really sure if it's a question about this theorem being too weak, or that we don't really know how to use it correctly in applying it towards the problem about the Epstein zeta function. But what we would really need is a modest exponential growth. Then a result of this type would be enough to actually understand the Epstein zeta function at the central point. And then, okay, so why can't we go here? I'm not really sure. Possibly we can. What I do know is that working on this theorem, what we use is that we apply the method of moments. So we calculate moments with this formula of Rogers, or we have to develop some new version of it, but it's essentially Rogers' formula. And calculating these moments, we see that if we allow even the smallest exponential growth, some moments will diverge. So given the method of proof here, the result is optimal. So with calculating moments, we cannot do better than this theorem. But that doesn't say that you cannot do better using some other technique. But at least calculating moments, this is an optimal result. And then one can, of course, ask how one should improve this. And at the moment, I don't know. But then there was this, before I end, I also want to address this other issue. There was something about, at the central point, you don't only need to understand the function hn, which was only half of the Epstein zeta function. You also need to understand hn at L dual, which is the second half. So there's something about the relation between a random lattice and its dual, also again in the limit of large dimension. And what one really would like to understand here is, of course, the relation of this hn function at L and L dual. But as a first step, we're trying to understand the distribution of the lengths of the lattice L and the lengths of the vectors of the dual lattice L star. And in order to do so, we have developed a new moment formula, a sort of generalization of Rogers' mean value formula that can handle mean values of expressions of this type. So this is a double sum where a certain number of variables belong to the lattice and a certain number of variables belong to the lattice dual. We have a formula for the mean values of these expressions as you take mean values over the space of lattices. However, these formulas are not super explicit in the sense that you again get an infinite linear combination of integrals over Euclidean spaces or subspaces of Euclidean spaces. And in this infinite linear combination, there are a lot of parameters and things. So it's a little bit premature to say exactly what we can say about the sort of question at the top here. But I can at least show you what we can get in some easy case. So in a first case, if you have one variable in the lattice and one variable in the dual lattice, then we have a rather explicit formula for such mean values. So pretty much in the same spirit as the formula of Rogers that I highlighted some slides ago. So you take a mean value over the space of lattices of this double sum. Then there are some first terms here, depending on what's going on at 0 of this function of these functions. And then there's an infinite linear combination of integrals over Euclidean spaces that are rather explicit. But instead of in the Rogers formula, you always get full integrals over Rn's. Here you start to get slightly more complicated expressions, and in higher moments you get even more complicated expressions, and that's why I don't really want to display them here. But somehow this is work in progress, and I hope that in not too far into the future I can report on something about also the main questions. But for now I think that I'll stop here, and I say just Thank you.
Good. Well, thank you very much. So, questions, comments?
Yes?
So in trying to solve an optimization problem, and the sphere packing problem is the most basic optimization problem. And so for this, there have been this linear optimization method of cone and lattice, and even so it's also a bit strange the way you stated E8 and E24 without citing the fact that it was the densest, but it was only very recently discovered. But so Sarnax and Sodergren, they say we suspect these are the densest, and so we look at this minimum, but it's only recent that we know it's the densest.
Right, but it's not as recent that we know that they are the densest lattice packings. So the most recent results are that they are the densest sphere packings, but knowing that they were the densest lattice packings is a little bit less recent, but also, yes, quite recent.
But nevertheless, so my question was, is there a way to bridge between the method of cone and lattice and what you are wanting to do?
Well, a very good question. I don't know.
Because it's really, okay, it's another optimization problem, so one should maybe look at.
Yes, but I don't really know how to make one method useful in the other. But yes, that would be fantastic, if possible. Yes?
Back in 2 dimensions, the hexagonal lattice has complex multiplication. If you assume you look at lattices which have complex multiplications or maybe real multiplications, much more restricted comparisons need to be done about that.
Right, but also somehow for the methods that I presented today to work, you need a full space of lattices in order to actually make calculations. So restricting to smaller sets is, of course, preferable in many ways, but then you need also other tools in order to actually do the analysis on those smaller sets of lattices.